Hey everybody. Today we're welcoming our very own DHRUV BALWADA. DHRUV is a Lamont Assistant Research Professor in Oceanography and Climate Physics at Columbia University's Lamont Doherty Observatory and a member of the LEAP Center. His research focuses on understanding and parameterizing ocean turbulence across scales, combining theory, observations, and machine learning in order to improve how turbulent processes are represented in climate models. His work spans observational analysis, eddy parameterization development, and the application of modern deep learning methods to ocean state estimation and model development. So, yeah, welcome, Drew.
So I'll try and hold the mic close to. I don't think it's fine. No. And is it working? Yeah. Okay. I'm going to try and hold this close to my mouth. If I drift, please, somebody just wave your hand and remind me. I gave a talk just a few weeks ago at Lamont, and I know that some of you were there. And so if you were at that talk, feel free to just leave or tune out because it is more or less the same thing, maybe presented with like slightly different details and so on. And most of the work that I'll be presenting here is obviously not just my own, but my collaborators, people who are in my group, and it's work of many people. And a lot of the work that my group and people surrounding me have been doing has been to do with machine learning and their applications in physical oceanography. I'm originally a physical oceanographer and have kind of started to delve more into machine learning partly after I came to Columbia and started to have some associations with LEAP. And so like LEAP has been a very critical part in my journey along this machine learning path. Maybe another thing to say is that as a group or in my work, we don't really develop new machine learning algorithms. We are very much applications focused, applying them to physical oceanography problems and seeing like where we can leverage all these new ideas that are coming up. Okay. And in terms of the scope of the work that we do, it mostly centers around ocean turbulence. And so if you are not familiar with these kind of pictures, ocean turbulence, broadly speaking, just means the chaotic flows that are present in the ocean. And these flows take place across a whole range of scales. And so this image here is a satellite color image of a region. I think this is in the Baltic Sea. And the shading or the different colors that you're seeing are representing phytoplankton bloom. And so regions that are green probably have higher chlorophyll than regions that are dark and black. And to give you a sense of scale, you can see some kind of speckles here. These are little boats that are moving around in here. So the size of this large pattern at the center of the slide, at the center of this image is maybe about 10-ish kilometers in size. And you can see that there's finer detail even within that. And if you keep zooming out, if you go to the scale where you're thinking about maybe one section of the North Atlantic, similar kind of flow patterns still remain. Okay. And all of this kind of brings us back to like how we try to think about our physical world, in particular, the ocean. It is composed of motions across multiple scales. And this is really beautiful, right? We look at these pictures, and whether you're a physical oceanographer or not, these are very captivating. But along with that beauty, there's also a problem, which is that when you want to model things that are happening at, let's say, scales up here, if you're a climate scientist or maybe somebody who's doing seasonal predictions, right? You care about things that are taking place on the order of maybe months to years, and length scales on the order of 1,000 kilometers. Whatever is happening here depends on everything that's happening all the way down to the smallest scales that's there. And these multi-scale processes, they're relatively complicated, and they interact with each other. So a lot of my work is focused on scales that maybe live down here in this time scale versus space scale diagram. These are in the ocean called mesoscale or submesoscale processes, and these processes talk to each other, but at the same time, they also project onto what's going on at the largest scales that's there. And so this is one of the challenges, is that like, how do you understand what's happening at these scales? But at the same time, how do you also understand like how these scales affect the largest scales? Okay, now one way that we do this is that we can build models of what's going on. So this is, it says climate models, but you could imagine a numerical model at any particular scale. the numerical models, the way that all the numerical models in the world work is that these are, in the simplest form, bucket models, right? You kind of divide your world into little buckets and things flow back and forth from one bucket to another. So this might be things like the amount of water or the energy and so on. And so a climate model that's trying to divide up the whole world into these boxes or buckets might look like that, where every single grid scale is roughly 50 to 100 kilometers in size. You might have some layering in the vertical as well. This is the kind of model that you'll run if you care about the long-term processes. But because you're dividing the world into boxes and each box has computations going on a computer, there's only so many numbers that you can fit into your memory or into your, even your largest computer. So you're limited to like how small you can make these boxes, okay? And whatever is going on at scales smaller than those boxes might have to be represented in some other way using some things that are called parameterizations. If you cared about the smallest scales, you could obviously zoom into a region, put all of your resolution there, but then you don't know what's going on at scales larger than the, the region that you zoomed into. But let's think about the climate problem for a second. So you divide the whole world into boxes. You in the sense like the entire world has many modeling centers. They make different versions of these models and they run them. And basically what we see is that all the models are able to produce something that looks Earth-like, but that's not enough because the demand on these models is much greater right now. The sort of society demands of them to make projections of what's going to happen in the future. And so when you try to make projections, or even before you're trying to make projections, when you just look at the model, you will find that all the models have some biases in them. So bias just means that you go observe something in the real world and the model doesn't look exactly like that. There is some kind of systematic shift. So these are biases in sea surface temperature. So let's pick this one example over here. You're seeing that there are regions that are blue, meaning that the model is on average cooler than the real world. And there are regions that are red, the models on average a little bit warmer. And as you go across models, all the models show biases, and there's a lot of similarities between the biases. And the fact that there are similarities seems to suggest that there's maybe something fundamental that we're missing over here. Otherwise, each model is a different version, right? Like, why would the same problem be showing up all over the place? So in addition to these biases, as I was saying, we use these models to make projections of the future. And we find that all the models give us different answers. And part of the reason for this is that so the models have to be forced with something, right? Like how the solar forcing might change, how the radiative forcing might change, how much CO2 we put into the system changes the climate system. And so there's that aspect, which is like, how are we as a society going to behave going into the future? And this variation is sometimes called scenario forcing. So like or scenario uncertainty. And so we can see that all the models are forced under different scenarios, and there's a huge range of projections that you get. Now what you can do is you can start to split up the uncertainty or the spread that's coming in from the fact that you have different scenarios. There is some parts that are going to come in from internal variability, right? Like the world is not completely predictable. There'll be just chaotic variations that are there. That's called internal variability. And then there is something called model uncertainty. So this is the spread in the projections that's coming from the fact that all the models are giving slightly different answers when they're run under the exact same experimental conditions. And so this is one way that we divide up uncertainty. And then you can look at what's the fraction of uncertainty at some time. I should say that this is the projection of the global mean surface temperature. In some ways, this is the easiest thing that you can try to predict, right? And so the fraction in uncertainty that you get, so at time that's now or maybe just a little bit into the future, there's a lot of uncertainty that comes from the fact that the system is chaotic, right? So the system is going to diverge from its initial conditions, and there is that. But there's also a huge chunk that's coming due to model uncertainty. So maybe if you're trying to make predictions that are just out to a season or a couple of seasons into the future, you're living on over here. And you can already see that all the models are doing something very different. As you go march forward in time, let's go to the end of the century. Most of the internal variability is not something that's important anymore. Mostly what matters at that point is, how was the scenario that you were running the model under, right? Like, how is your external forcing? What is that doing? And we know that's uncertain. We know, we don't know what humans are going to do. And so even to the end of the century, what we see is that about 50% of the uncertainty is coming from model uncertainty and another 50% that comes from scenario. And this is a little bit troubling, right? Because we know our models are doing different things. We want to make projections of the future. But even if we go really far into the future, right, the fact that the things that we don't know about what we are going to do as humans, they project onto the uncertainty just as much as the errors in our model. And this is something that we, hopefully as scientists can try to fix, right? We believe that we know something about the physical world. We believe that we can model it, and still we can't, right? So what is missing over here? One way that we can try to figure out, right, like what is missing over here is trying to look at maps of this uncertainty, where it comes from. And so now it's this initial diagram just popped up, and each column here are different categories of uncertainty, and each row is different time. So this is like right ahead of when these models were started, and this is at the end of the century. And basically, you see that as you go to the end of the century, internal variability is not a large part of the uncertainty, versus the scenario uncertainty does start to become a large part, as you expect. But if you look at model uncertainty, even to the end of the century, there are regions in the world where the model uncertainty is still large. And a few regions that really pop out are the Southern Ocean and the North Atlantic. And from other work, we now understand that a lot of this uncertainty is coming from what the ocean is doing in these particular regions. I mean, the other factors like how the ocean projects onto the atmosphere and so on also matter, but the ocean is kind of one of the key components of where this uncertainty comes from. And then, we may ask, like, why is the ocean so uncertain in these places? And one way that we can do that is by running all the models under same forcing. And so this is a particular kind of MIP, right? These are model intercomparison experiments. In this MIP, so you only take an ocean model, you force it with some prescribed forcing. And in these cases, what the forcing that's applied is like some surface fluxes of heat and fresh water and so on. And then you ask the question that, okay, where is the ocean going to take up heat? Because, we care about heat uptake in the ocean because that impacts climate. And you see that if you look across an average of all the models, there are regions that are redder. This is where the ocean takes up a lot of heat. So it's often in the high latitudes. These are regions where the interior of the ocean is connected to the surface. And so there's a lot of heat uptake in those places. But if you at the same time look at where the models are most uncertain or most different from each other, the same regions line up. So the regions that we know are most important for heat uptake are also the ones where we have the highest amount of uncertainty. We can break this up further and try to understand that, okay, what were the processes that were responsible for this heat uptake in these regions? And we can divide them into kind of two broad buckets. So we're going to look at how much heat is, being taken up, or the tendency of heat in the ocean from the processes that are resolved. So this is stuff that's larger than the ocean model grid scale. So this is stuff that you can maybe say that, I can kind of model. My model can actually resolve this stuff. And then there's all the stuff that's smaller than the grid scale. This is stuff for which I have to build empirical sort of small parameterizations or models, because the numerical model itself cannot resolve this. If you come from the atmospheric world, sometimes the distinction is that these are called the dynamics and these are called the physics of the model. And so basically, we're going to try and do that dynamics versus physics split. And when you do that across a bunch of models, so what we're looking now at is some average heat uptake in a region and which of these processes contribute to it. And so the black dot is the total, some measure of total heat uptake. The red dot is the amount of heat uptake in this region that's coming due to the resolved flow. The dashed line is 0. And basically, most of the models in this region, the heat uptake that takes place is due to the resolved flow is roughly 0. But the total heat uptake is not 0, right? The black line is quite a ways away from this dashed line. And what we're seeing is that it's the parameterization, the stuff that the model doesn't resolve, that is responsible for most of the heat uptake in these important regions. And so this gives us a clue that, these parameterizations have some issues with them, which is why the model's uncertain, and which is why, maybe we are having projections and we are having problems with biases, but at the same time also having problems with future projections. Okay? So given this, we set out to try and figure out if we can make the situation a little bit better. This was a few years ago, and we already have these things called high resolution models. So maybe one solution is that, okay, let me just make the resolution finer. Let me just resolve these processes that seem to matter. And so we can run high resolution models, but the problem is that as you increase the resolution of the model, the cost increases quite dramatically. So every halving of the grid step, so if you go from 100 to 50 or 50 to 25, every time you halve that, the model expense goes up by an order of magnitude, because you would have to sort of simultaneously halve the grid scale in the X, Y, and Z direction. And then also you'll have to take finer time steps. It's not like a perfect linear relationship, but roughly there's a doubling of an order of magnitude increase in cost with a halving or resolution. And this is a nice picture from a very high resolution ocean simulation that was done about a decade ago. So in this case, the grid scale was roughly 2 kilometers. And the cost of this model was 3,000 core years of computation. So this means that if you had a 3,000 core HPC system, you would have to run the simulation for 1 year. And this was ocean only. There's no other, the atmosphere is not being calculated, which actually is a very expensive part of a climate model, right? And this was at 2 kilometers, which we know is not even resolving everything that we want. And that's for 1 year, right? When you run climate simulations, you want to do decadal predictions, maybe like a century down, right? How is this going to help us with that? So we know that just doing brute force is probably not going to get us there. But we said that, okay, these models have these small scale features that are being resolved, and they seem to be a little bit more reliable than if we don't resolve them. So can we leverage the data from these high resolution models to somehow make our coarse resolution models better? That's the challenge over here. And this is where this big M-Square Lines consortium project comes in. We were trying to do this for different components. My focus was more on the physical oceanography side, but there are people working on the atmospheric side and the CI side as well. And the question is that, can we leverage high resolution models to make the parameterizations better? Okay, and the way that we are going to go do this is following this general recipe, which, there was some like inkling of this is how we should do it when M-Square Line started, but like over the time we have maybe figured out which pieces are the most important and so on. The general idea is something very similar to large eddy simulation framework, if you're familiar with that. If not, I'll step you through it. And we're going to look at one equation in the model on the left to kind of give you some mathematical flavor. And on the right, I'll show some pictures corresponding to the different variables. And so I'm going to focus on the buoyancy equation in the model or the density equation in the model. And if you start out with a high resolution model, you can solve this equation, which looks like this on your high resolution grid. You get a lot of fine scale features in your variables, like you have all these eddies and fronts, and we're going to take this as our ground truth. Now, what we can do is that we can apply some filters to these equations. So now the question we're asking is that I don't want an equation at my finest scale. I instead want an equation that describes a large scale flow, but in this fine resolution model. And why I want to do this is because my eventual goal is that if I believe my high resolution model to be good, maybe I want my coarse resolution model to look like the large scales in a high resolution model. And so this seems like a reasonable target. And so we write down an equation for the large scales from this fine resolution model. And as soon as we do that, we see that most of the equation looks exactly the same. And if this term was not there, it'll be exactly the same as the other one with just a notational change. But now there is this extra forcing that comes in. And this extra forcing is the thing that the parameterization is trying to model for you. And since we have high resolution data, we can apply filters, estimate the large scales. We can even compute these terms. So these are the things that we want to parameterize, or what you might call the subgrid forcing. And then the goal of a parameterization is to be able to predict maps of the subgrid forcing in terms of the large scale variables. Because right now, this equation has variables at two scales, the barred variables, which my model can resolve, and the primed variables, which my model cannot resolve. But if I can write down these primed variables in terms of the large scales, then I have a closed equation set. And that closed equation set is what I can solve on my coarse grid as my climate model. Okay, so this is the thing that we want to learn. And instead of going about it the traditional way where we make some guesses, we're going to try and learn this using a machine learning model. And if we And so we don't have to do it at a single scale. We can also do it across a range of scales, because maybe, when I finally implement this thing, I don't want to work at just one fixed scale. I want to have some flexibility in changing the resolution of my coarse model, and so on. And so this would be the coarse resolution model equation. It looks exactly the same as the previous one, where instead of the subgrid terms which are being diagnosed here are now being modeled using some function g, which is what my machine learning model would be. And if everything works out, hopefully the coarse model variables would converge to the large scales of the high resolution model. And if I believe that my high resolution model is better behaved, then this is a good thing to do. Because right now, if you don't model this well, that convergence doesn't take place. Okay, so this is the problem. And in this work, in some of the work I'm talking about right now, we particularly focused on a range of scales that are called mesoscale eddies. These are scales which are roughly about 10 to 200 kilometers in the ocean. And the reason we care about them is because most of the kinetic energy in the ocean is part of these scales. And so if you somehow, try to figure out how much kinetic energy you have at different scales, it will turn out that these scales have most of it or a lot of it. Okay, so they are quite a dominant presence in the ocean. And since they have so much of the kinetic energy, they also control the transport in the ocean a lot. So we care about how heat, tracers, nutrients, carbon, all those things are being transported. They are being transported by the flow, and the thing that has the most kinetic energy probably projects most strongly in which direction the transport goes in, right? They have other important properties. So the way that these eddies come to be is through this thing called the baroclinic instability mechanism. The idea is that the ocean is forced at the surface by the atmosphere. So these are wind-driven forcings. There's some radiative forcing. So most of these things will create large-scale gradients in the ocean. And so you will have a north-south temperature gradient. The wind might push the ocean down in one side, or push the water down in some places, pull it up in the other places. And when it does that, it modifies the interior stratification. And so interior stratification means that if you look at density surfaces in the ocean, they are sloping. And what these eddies do is they extract that energy from the sloping isopycnals and try to flatten the isopycnals out. And when they try to flatten the isopycnals, they can change the stratification that you would guess just based on forcing. Okay? And they have other properties, like they have an ability to transfer energy between scales. And so you can have these instabilities forming at some scales that correspond to their dominant growth scales. If you've ever taken a class in like dynamics, we often study about instabilities and they grow at a particular scale. But then once they have grown at the scale, that energy can move across scales. And so they can do that as well. And another reason that they are important is that, or these scales are important, is that the typical grid size of a CMIP class ocean model would be about 100-ish kilometers in the ocean. Some might go to 50, sometimes you might even go down to 25, but that's sort of the limit right now. And so the model resolution lives right around what these mesoscale eddies are doing. So most models don't resolve them. The ones that do resolve them kind of resolve them partially. And so that's another reason to focus on these scales. Okay. Okay, so now we are not the first ones to solve this problem or try to approach this problem. People have known that mesoscale eddies are really important in the ocean for all the reasons I just mentioned. And people have also known that if you don't parameterize them, your ocean simulation does not look right. And so there has been a lot of work on this. And in particular, one of the key papers was in 1990 by two scientists named whose last names were Gent and McWilliams. And they came up with this parameterization where they said that, okay, we can't just like arbitrarily throw in a function for this, right? So if you have ever built parameterizations, so taking a step back, if you have ever built parameterizations or if you've worked in that world, a very common thing to do is that when you don't know what a term is, you try to replace it with something like diffusion or viscosity, because you kind of believe that the small scales are like on average just mixing things around. And so let's try to do that. That's the simplest guess. And that's what people were doing. And the ocean models had many, many problems associated with them. So they realized that, okay, that's not going to work out fully. We are still going to do some diffusion, but you have to constrain this diffusion in particular ways. And the ways that you need to constrain this has to come from some physical understanding of what's going on in the ocean. So as I was saying, these eddies will extract energy from sloping isopycnals. And so what does the sloping isopycnal means? It means that if you look at a fixed depth, you have some density gradient across that depth, right? And so if you just applied diffusion on that depth, what the parameterization would do is that it would just mix up the density that's there. But turns out that these scales do not actually mix up density. They just flatten the isopycnals, which is a slightly different process than mixing the densities around. Because if you were just mixing the densities, ultimately you would end up with the same density everywhere in the fluid, right? Versus if you're flattening the isopycnals, you still maintain the volume of that you have at different densities. It's just that they have been rearranged in a different way. So, these guys were clever. They figured out that, okay, simple diffusion is not going to work. What you need to do is you need to do something like diffusion, but put it in the form of an advection. And so advection by itself is a volume conserving operator. And if you do that, then things will be nice. Your volumes won't get mixed, and volumes not mixing is, as an oceanographer, really, really important. Okay, so this was a step change in how things work. So they came up with this, and they said that, okay, we're going to add some advection in, but this advection will be added in terms of so you can always put advection in terms of a stream function. But at its core, the stream function still has some diffusive aspect to that. Because ultimately, you're rewriting terms, but there are some terms that you still don't know. And so the things that you don't know, you're going to write them out as diffusion. And this is quite problematic because, as I was saying, right, like the real world is not diffusive. And this is the place where we want to inject machine learning. So we said that, okay, we believe everything you're saying. There's a lot of observations. There's a lot of evidence that everything you're doing is right, except this step over here. And so this step we're going to replace with a machine learning model because we think diffusion is not a great descriptor or the right operator for this part. Okay. Now we need to choose a machine learning model, and there's many, many choices, right? Even before machine learning models came in, we were applying something like diffusion. Now suddenly this entire axis has been exposed to us. And so what do you pick, right? Do you do something that is really complicated, like a deep learning or CNN model, or do you do some more like equation discovery techniques? These are basically regressions to some terms in the equations. Trying to build rough functional forms for things? Or do you do some simple neural networks that live in the middle? In our work, we decided that probably something this complicated is not necessary for the problem. And this was just based on previous work. We saw that, yes, you can just learn things this way, but if you made your model simpler, you were still able to learn things. So why go for more computational cost when you can do things at a cheaper, just more cheaply? And the reason you want to do things cheaply is because, ultimately you're going to put this in a climate model. If you now attach a machine learning model to your climate model, that's just as expensive as the machine learning model to start with. You haven't really made much progress, right? The goal is not to make the model just better. It's also to make sure that it doesn't become extremely expensive in the process of making better. Because I could have made it better just by running it at high resolutions, but that's, not feasible. So we try to live over here. We could probably move even in this direction, but it's not something that we have done yet. Okay, so we're going to live with things that are called ANNs or MLPs. These are very, very simple models. And we're going to do some more things. So we can train a simple ANN or MLP, and it learns from our data. It learns from the data that we show it. And then as soon as we try to apply it to some new data set, it often fails because you're trying to go out of distribution. So if you're doing ML, this problem out of distribution is not great. So what we're going to do is we're going to try and change the structure of this thing a little bit so that a lot of the expected data becomes in distribution. And we are going to do a few things to make this possible. Okay, so one, we're going to try and make all data sets in distribution, even the ones that are not seen. And we're also going to try and build in some more physical aspects into the problem. Okay, so how are we going to do this? So this is the thing that if I had blindly used an ANN, it would have looked like this, right? I would have some function g theta. Theta are the parameters that I want to learn. And what goes in are some inputs. I need to choose those inputs. right? So maybe based on my physical intuition, I'm going to choose some input. So you always need to do that. So we did that. Another thing that I'm going to do is that I realize that I'm solving a physical problem with known dimensions, right? And so I want to create a ANN which respects these dimensions. And so, for example, or I'll tell you what we did, and it makes sense. So we know that u prime b prime over here has dimensions of u multiplied by b. And so one non-dimensionalization that we can pick for this is that we can say that, okay, the large scale velocity gradients and the large scale buoyancy gradients, which are present on the coarse model grid, have dimensions of velocity and buoyancy in them, divided by a length scale. And if I take a length scale squared, this entire prefactor here has the same dimensions as the thing on the left side. Okay. And then to my ANN, if I only give it inputs that are non-dimensional, right? Like I'm putting in non-dimensional numbers, I guess I expect that it won't just create something that's dimensional that's coming out, right? So I've pulled all of the dimensionality out of the machine learning model into this prefactor. And then the things that are on the inside are things that are non-dimensional. Okay? And the way that I make things non-dimensional is that I first chose that the velocity and buoyancy gradients are going to be the input because I think they physically matter for this problem. And dividing them by their norms allows me to make them non-dimensional. Okay? Hopefully that's clear. If not, just to kind of repeat it, I'm not going to take a model by itself, sort of blindly. I'm going to do some non-dimensionalization so that the model can't just, arbitrarily create dimensions for me. Or sort of, I want to get an output that's in some units. It doesn't just give me outputs that are in totally different units. Another nice thing that happens over here is that the inputs are non-dimensionalized in such a way. So let's think about buoyancy gradient, right? It's a gradient in 2 dimensions. Let's say it's a gradient in 2 dimensions, x and y. So there's a dBdx and a dBdy term in it. If I divide dBdx and dBdy by their magnitude, each of those dBdx and dBdy divided by their magnitude can only exist between plus and minus 1, right? I've sort of constrained myself to be in that range. And any new data that will ever be seen by the system is always going to live within that plus and minus 1 range. Right? So now I've also solved the problem of going out of distribution. So at least numerically, things will never go outside plus and minus 1. There's still the problem that, within that plus and minus 1 range, maybe I have not, my original training data set has not spanned the entire range. So that can still be an issue. But at the very least, I'm not just trivially drifting out of that unit sphere or that unit line. And we found that was quite important. We did some other things like the fluxes have some directionality, and then the large scale gradients have some directionality. And so you can use so instead of making predictions in the X and Y directions, we take the relative directions, and that allows us to be coordinate invariant, which means that if you had data where most of the training samples were, let's say, pointing in the X direction for whatever reason, and now if you go to a new training data set where things are mostly pointing in Y, but none of the physics have not changed, you've just turned your system around. Living in a system which knows about that or is invariant to that matters. And one way to do that is to go to this coordinate invariant. And another thing that we did was we, by some empirical testing, figured out that if we want to make a prediction at a single point, using data just at that point is not sufficient. So ocean turbulence, right, is like whatever's going on at one point is probably being influenced by its neighbors. And so we try to figure out how large of a window do you need information to come from. And by testing, we figured out that a window size of about 3 or 5 points is more than enough. If you go beyond that, the scale doesn't improve very dramatically. Okay, so these were the principles that we put in our design. And when we did that, now we have a model, we trained it on some data set from a high resolution model. Let's see how it does. So this is the diagnosed subgrid flux, one component of it from some high resolution model. And this is the prediction that you get from the ANN, basically indistinguishable. You can compute different skill scores like R square or correlation, and they're generally quite high. There is some tendency to decrease as you go to larger and larger grid scales, but let's not worry about that for a second. This is the field that would be predicted by the traditional diffusive parameterization. Once you have tuned it to this particular data set. Okay, I should say that this prediction here is coming from some training that was done over a very diverse range of data sets. So like this data set was part of that distribution, but it kind of learned many, many things and can do really well across all of them. Versus if I take this image and say that, okay, I know that GM can't do well across, or the traditional parameterization can't do well across the whole range, but let me just get the right answer for this particular situation that I care about. This is what you get. Obviously, these patterns are too complicated for those diffusive operators. And we know this by design, but here I'm just showing you an example of like how bad the situation is. And you can obviously compute R square and correlation, whatever you want, they're going to be on the very, very low side. So this is the skill that you get in what might be called an offline setting. We're just predicting the subgrid fluxes. But let's go back. Our goal is not to just predict the subgrid fluxes. Our goal is a little bit more. Our goal is to build a model where the coarse scales look like the large scales, right? So in this world's jargon, this thing is called offline scale. So you are not actually plugging your parameterization into a model to test it. You're just testing it on some data set that you have withheld. Making it work in a coarse model is called online scale. So we don't want just offline scale. We also want the model to perform well online. And that's the next thing that I'm going to show you. And that's over here. So we did, at this point, we have implemented the parameterization in a bunch of different setups. I'll show you an example of a single one to get like the main character points across. And then we can talk a little bit more about the other ones. And so this is a very sort of simple ocean setup that is used for understanding ocean dynamics, doing ocean modeling. It's called a two-layer double gyre setup. And so the idea is that you're thinking about something like maybe the North Atlantic Ocean. There's a certain profile of winds that blow through that, and you get some gyres that form. And so, for example, in the North Atlantic, we know there's a Gulf Stream. That's the Gulf Stream over there. You have a gyre on the southern side and a gyre on the northern side. And the other thing that we also know about the North Atlantic dynamics that's important is that there is some stratification in the ocean, right? So the ocean's not constant density. And to bring that flavor in, we have a couple of layers. And so this is like the minimal model that you can go and start to test your parameterization in. And when you run this model, let's focus on the first two pictures first. So this is this is the mean sea surface height. So you run the model, average over many, many decades. This is what the mean sea surface height looks like. So on the southern side, there's highs, northern side, there's lows. This is what a low resolution model would look like. So broadly speaking, it is doing the same thing. It knows there are gyres and so on, but there are a lot of problems in the details, right? Like it's produced this extra eddy over here. And that's one of the problems with this particular setup. Now, if we plug in our ANN parameterization, we get this. So we get something where the mean state or the biases in the average sea surface height are significantly reduced. For this toy problem, I could have done the same thing with Gent and McWilliams as well. So this is, if I tune Gent and McWilliams to this particular setup, this is the mean sea surface height that I would get. So none of them are perfect, but generally they're much better than the low resolution state, right? So I have not fully converged to this, but I've gone much farther than if I did not have the parameterization in there. Okay, but sea surface height, mean sea surface height is not the only thing that I care about. I care about other aspects in the problem as well. I told you that kinetic energy is important in the ocean. It controls the transport. And so let's look at some pictures of what happens with kinetic energy. One thing to point out is that these plots are all on a log color scale. So, sometimes the changes might seem small, but actually they are orders of magnitude difference. So this is the high resolution model, looks a certain way. Low resolution model, there's some kinetic energy, looks quite distinct from the other one. This is if you apply the ANN, and this is if you use the traditional diffusive parameterization. And basically what you see is that when you're using the ANN, you get a kinetic energy structure that looks very similar to the high-res one. Again, it's not perfect, but if you contrast it to what would have happened with the tuned GM, right? The tuned GM has killed a lot of energy in many, many places where I expect there to be energy or flow variability. And this is a known problem. So this was, one of our targets when we started with this work, which is that we knew that traditional parameterization of mesoscale eddies have this limitation where, because they're diffusive, they end up diffusing the flow when you tune them to get the mean state right. Okay, so why did this happen? Again, we don't have a definitive answer, but we can suspect something. So the way that the mean states and the variability is being generated in the model is that there is some interaction going on between the mean flows or the resolved flows and the subgrid. And sometimes these are called eddy mean interactions. And so what we can do is we can go and start to diagnose some metrics corresponding to these interactions. And these interactions were not, the machine learning model was not made aware of these things. If it's doing something right in this case, it's just something is learned from the data. And so this is the picture of eddy mean interactions. They're both the same. Let's just focus on the top one. This is how the eddies smaller than some scale interact with the large scale. And you see that there are some patterns. The regions that are red is where the eddies are pumping energy into the large scales, and blue is where the eddies are extracting energy out of the large scales. And this is kind of the underlying turbulent process that is shaping a lot of what's going on over here. If you turn on Jensen-McWilliams, it can only ever extract energy. That's what diffusion does. And so it basically gives you this extremely blue map. And this is, kind of being reflected here. Your kinetic energy gets killed a lot. This is the map that you get with the ANN. Again, it's not a perfect match, but it's qualitatively much similar to the original data than what GM was doing. And if, again, this is a log scale. So, small color differences are actually orders of magnitude differences over there. And so we suspect that, part of the reason that things have gotten better is because these small scale interactions are being represented better in these setups. And that's why, you're starting to see improvements across multiple metrics simultaneously. Okay, and I think we're coming close to the end. I have one more thing to talk about and then I'll finish. So what I was showing you right now is this simple toy problem here. At this point, we have at least implemented and run the model. And so we implemented it in a certain ocean model, but then we have evaluated that ocean model across a range of complexities. So there are, if you ever think about the medical sciences, there are, the mouse models, which are your toy problems, or we shouldn't say that, but these are the problems where they do like a lot of their testing. And then eventually you slowly want to scale up onto the most complex things, right? So these are like the mouse models of oceanography. These gyres, some little channels. You can go to setups that are more complex, where maybe you have more topography, you add more stratification components in, and then these are the most complex ones. These are fully forced ocean models that are forced with an atmosphere, and there's a whole lot of biases that come in. And so at this point, we have evaluated across the whole hierarchy. We can say that at least up to this point, so it is there are model improvements, and the model improvements that we see at the simpler setups, they seem to be present even as you go to more complicated setups. When you go all the way to the final ones, things like you're not killing too much eddy kinetic energy and so on still remain. But these models at the highest complexity have a lot of components. It's not just, it's not that mesoscale eddies are the dominant player in this. There's many, many subgrid processes that all interact. And so if we changed one, it doesn't mean that we are suddenly going to see the model improve, because originally, like the way these setups are built is that it's not just a model that's built. You build a model and then you build a parameter file. And the parameter file is hundreds of parameters that are tuned to give you something that looks on average right. And so if you now change one parameter and don't change the other ones, you don't expect the model to improve. If anything, you expect it to get worse, right? And so that's the state that we are at right now, where it works, it's stable, right? So stability is great. A few years ago, like the entire talk could have been about the fact that we made our model stable, right? But I think we have gone a little bit past that. We're generally very stable now, or at least we have figured out situations in which things go unstable and we know how to account for them. Okay, so in the last 4 or 5 minutes that I have left, I want to go a little bit past that, the fact that we can make this model work across a hierarchy, right? So the end goal over here is not to just build a model that works on a single setup for a single forcing. We want to be able to build parameterizations that are reactive to forcing. So for example, right, if we were thinking about the climate problem, the radiative forcing is what's changing. And so you want to build a model, you could maybe even easily build a model that, given the present day forcing, tells you what the present day state is, right? Maybe not a climate model, but you could definitely build some simple model, right? Like let's say your model was just a box model of the average global temperature. You could tune it to the present day setting. The hope is that you can build a model which, when you change the forcing, tells you how the system is going to change, right? Like that's what we build models for. It's not to just attach ourselves to the present world. So we're going to try and see what happens to our modified ocean models with changing forcing. And we are going to focus on one particular case. This is a situation in the Southern Ocean. So the Southern Ocean winds have been changing over maybe since the 1970s or so on. There's something called the Southern Annular Mode, which is a measure of how strong the Southern Ocean winds are. And that index for that SAM mode is slowly going up. So we suspect that the winds are increasing in strength. And as the winds increase in strength, we want to know how the ocean is going to react. And it's not a simple problem. It's not as simple as that your winds go up and your ocean linearly responds. There's a lot of nonlinearity in the system, and different models at different resolutions with different parameterizations give you different answers. So what happens when we try to build a toy problem of these increasing winds? So the way we're going to do this is we're going to take a little channel, set up the stratification and the forcing to look Southern Ocean-like. So there'll be some winds blowing at the surface. There'll be some heating, cooling at the surface that look Southern Ocean-like. And we'll add some topography in, which is not shown in this image, but that's quite important for the Southern Ocean dynamics as well. You're going to do all of that, run this thing. And we're going to first, let's not worry about our parameterization. We're just going to run this setup at 2 different resolutions. And so the black line here is the transport. So the transport tells you how much water is moving from the left of this picture to the right. This is essentially like a cartoonish representation of a current called the Antarctic circumpolar current in the Southern Ocean. It's very important for transporting heat around Antarctica and taking it from one basin to another. So the strength of that matters. And if we change the wind, so we are going across a large range of winds over here, we see that there is some change at high resolution. And remember, we are thinking of high resolution as a ground truth. If we go to a low resolution model, we still see that there's an increase, but the response is quite different, right? You maybe start out at a slightly lower transport at low winds. Once you go to high winds, the transport becomes quite a bit larger. This is a large parameter range. If you were, let's say, living around here, which happens to be roughly the wind stress that are present day like, the slope of this line is quite different, right? So one model might tell you that, okay, there should be barely any change. The other one will tell you that, okay, there's a factor of 2 change in transport. There's also a corresponding overturning in these models. Let's ignore that for now. So that's what happens if you just run the model at 2 resolutions. Now, if you run it with machine learning parameterization, so this is the parameterization that I have, plus other ones that have been developed in M²9. So in this setup, there's 2 parameterizations that matter. If you turn both of them in, you can get this response. So you can perfectly match the high resolution model at a 50-kilometer resolution. And so this was one of the things that we were looking for, right? That we wanted to be able to get the right response in these models with the parameterizations at lower. So yeah, I think you get the point. We also tried it across a range of resolutions. So we didn't want to be able to do it just at 50 kilometers. Climate models would have different scales in them. If you're running your simulations, you might choose different resolutions. What we can show at this point is that across a range of model resolutions, we can get the response to look like the high resolution model. And this is quite exciting. And obviously, we're working on this more, trying to test out that, was this just by chance in this setup? Like if we go to a different setup, let's say if we care about the changing response in the gyres to winds, is that going to be right or not? We don't know yet, but at least in this one, where the response really matters, we get things that look right. And it's quite an exciting place to be in. Okay, so I'm going to end here and just give you a short summary, right? So what we figured out in our work is that if you balance machine learning complexity with some in physics informed, right? In this case, physics informed was that we stayed within the broad framing of the parameterizations that were traditionally there, right? We added in some other things like non-locality in the model or this non-dimensionalization, right? So doing all of those things do allow us to build models that work quite well across a hierarchy. These new models, so when I'm saying model now, I mean the machine learning model plus the numerical solver, are able to reduce biases and show many signs that seem to suggest that maybe they can also respond to forcing in appropriate ways. There are still some things that need to be tuned. Things don't just work completely out of the box, but at least when you tune them, what we find is that, let's say you cared about 3 metrics. If you tune only on one, there are improvements in the other metrics simultaneously. With traditional parameterizations, that doesn't always happen. So if you tune for one metric, often the other ones are getting worse, and you kind of have to, it's like playing whack-a-mole, where you're trying to bang multiple things down at the same time. Here, that seems to naturally emerge. And we think that part of the reason that's happening is because we have, or these parameterizations have learned something about the internal dynamics of like how the resolved flows and the unresolved flows interact in detail, and knowing that thing in detail helps. And overall, the path that we started up on was that we wanted to use high resolution models to improve our low resolution models, and we have made some progress in that direction. It seems like these new parameterizations are significantly better than the traditional parameterizations. There's a lot of work that needs to be done, but so far the path seems quite exciting. All right, thank you.
Thank you so much, DHRUV. Does anybody want to open up with the first question in the room?
Thank you, DHRUV. It was a very clear presentation. I had a question about those physics-aware ANNs. So I know there are some very sophisticated kinds of, say, ANNs and CNNs that try to enforce symmetries and equivariance and directional symmetry. I would like to ask if you're looking to try to incorporate those more sophisticated architectures, or you're very happy with that because it works well, and if there's a need for like even more physical or even more symmetry respecting architectures in those cases.
Yeah. Okay. So I'll try to answer the question a little more broadly than just the symmetry respecting architectures, right? So baseline, every model is just a representation of something that's happening in reality, right? So you can always make it better, right? And bringing in new architectures is one way to do that. In our case, I didn't go into it too much, but we build in coordinate invariance in a slightly different way. Rather than putting this into the architecture, we put this into the way the outputs are shaped. So the outputs are not just predictions in the X and Y direction, they're rather predictions in a projected direction. And so that takes care of it partially. And so in our work, I think going forward, right, like the things that are maybe the most important to improve, I feel like the coordinate invariance is not the biggest challenge that we are facing right now. I think the biggest challenge that we are facing, and I was not able to get into this, is that when you make these predictions, these, for example, at these scales, they look pretty good, right? The color bar is such that it's showing the largest patterns over here and it looks very good. If you zoom in, you start to see that there is noise that's present at the finer scales. That is not visually present, and it's not like the dominant thing. And in this case, we get a little bit lucky because the equation in which we're doing our parameterization has this property where if there is noise, it just gets cascaded to smaller scales to dissipation and gets left out. If you were in some other equation where the energy gets cascaded upscale and you have some noise, the noise will start to impact the large scales. And so one of the things that we want to, I think, push in a little bit more is to keep the computational costs the same, but be able to reduce the errors in more of the details. And there's, I think, multiple ways to try this. Improved loss functions is the simplest one. I heard a talk yesterday where somebody was talking about how you can make the optimizers actually a little bit better. And that is another way to get to better solutions. So that for us, like that's one of the major goals. And then also the other thing is that we're sort of happy-ish with these setups for now. I think we are now trying to figure out problems with the when you go to online things. And so, I'm sure that some things get better, but also some things do get worse. And we're trying to figure out if there's some things about maybe the boundary condition or the training data, where it comes from, or there's some inputs that are missing that are not part of this, like, well, how to explore along those axes.
Very interesting. Thank you.
Any other questions in the room or on Zoom?
Do you typically take time variation of the data into consideration when you train? As in, does it matter if the instantaneous snapshots are in a particular sequence, or can you just jumble them up when you train them?
In our case, we just jumble them up. So we are not taking care of temporal variation. And so it's not built into the model. But since the model is learning from the large scale state, and the large scale state in the training data or in a course model is going to be temporally coherent, there is some temporal coherence that automatically comes in. But it's not coming from the small scales themselves. It's coming from the inputs being temporally coherent. In ocean or a lot of turbulence problems, right, the space and time scales play together really well. So if you go to, for example, larger spatial scales, the time scales get slower. And so I think that factor is helping us out over here, where we don't have to explicitly account for the time variability.
Thank you, Drew. I have a question is for the high resolution simulations for the eddy kinetic energy. The high resolution simulation usually give overestimate, which means that eddy kinetic energy will be higher, much higher than low resolution, as well as for the observations. So for your method, the machine learning also learn this kind of errors from the high resolution simulations? How you deal with it?
Yeah, that's a good question, and there can be another talk given on that topic. And so, yeah, I think that's like a really good point, which is that these models are only as good as their training data, right? So we train on something, and then we can do about as good as that. And I had a bunch of slides after, but then I realized I didn't have the time, and I'm not going to show you them right now, but I'll just show you one slide to give you a sense of the situation. So this is again, a kind of model intercomparison experiment done across where they evaluated a bunch of high resolution models. And what's shown over here on the y-axis is an estimate of the variability at different timescales. And basically, all of these models call themselves high resolution. They have more or less the same grid size, but there are still a lot of tuning coefficients that go into high-res models, showing that there's a range of variability that's present. So for example, wherever you look, right, like up here, you have about an order and a half range in variability. If you look at the finest scales, it's about 2 orders of magnitude. And so, yeah, our high resolution models are not perfect, and one needs to go to observations to try and make these better. And in the work that we do, we try to do that a little bit. I didn't have time to get into this, but hopefully, over the coming year, group members can give presentations on that.
Hey, great. If anybody on Zoom has a question, you can feel free to unmute. Or happy to take any other questions in the room.
Thanks for the talk, Dhruv. I was wondering that, from your ML models, you found that, for example, diffusion model was not good enough, and then your ML models were able to correct for it, right? Especially from the kinetic energy plot, which I found really interesting. Just wondering if your results from the ML models, can that somehow inform back the traditional approaches in the mathematics? Can it kind of tell us what other additional correction we can put? So diffusion and I don't know, something else, and maybe that will improve the traditional model. I mean, I know that equation discovery is a way, but do you think of anything else?
Yeah, I'll try to add a little bit on to the equation discovery aspect. Yeah, so as you said, for people who don't know, right, like the simplest kind of next step is to discover or fit an equation to whatever data you have. And you can do that, but maybe let me say a little bit about what was the extra things that this thing learned, which diffusion didn't do, which was helpful. So one thing that diffusion does is that diffusion is a down gradient parameterization. What that means is that if you have a directionality of your gradient, it only parameterizes a flux in that direction. So there's a cross gradient direction as well. That's important. And so one of the things that our parameterization has is that it learns the cross gradient component as well. And in some convoluted manner, what this work has shown us is that that cross gradient component is not insignificant, because in the past what would happen is that people would get to this point, like people realize that there are cross gradient fluxes, but they would say that, oh, the cross gradient fluxes are not important because the down gradient is all that matters. And there is some like deep rooted implicit bias in the community that has led to that. But what this is showing is that, yes, maybe if you parameterize it, things can get better. So that's one. The other thing that's interesting is that we have not constrained our models to be even on average dissipative. So apart from the cross gradient component, the other thing is that even in the along gradient direction, you can have fluxes that go down gradient, but also that go up gradient. And up gradient flux would be saying a little bit like saying you have negative diffusivity. And in the past, people never attempted that because, again, there's just this belief that if you have negative diffusivity, your model is going to blow up. And it does. But what this is showing is that, yes, if you just arbitrarily put in negative diffusivity, you can tune it up that the model will eventually blow up. But maybe there are some ranges that are not purely positive in which the model can still stay stable. And so if you're a mathematician, you can try to now figure out if there is like some space that's like farther than just that zero limit for your diffusivity that can still give you stable solutions. So I think that's maybe a direction to go into.
So yeah, so this work can actually like lead people to actually develop better traditional models. That's pretty cool. Thank you.
Hope so.
Sorry, just following up on that really interesting discussion. Have you faced like barriers in the field of, presenting the statements you just made that go counter to people's intuitions? And how have people react to that? Have they been skeptical, like this is just machine learning mumbo jumbo, or?
I think overall the field's been a little bit more receptive than we would expect. The ocean modeling field is very small, so there's not that many people. Like, one side of this room is probably enough. There is, there are some people who are like, okay, this is cool, but it's not for us. There are some people who are saying that, who might say that, like, the only thing that's going to convince me is like, okay, I don't care about any of this. Get this one right, and then we'll talk. Right, so that's kind of maybe the perspective of NCAR scientists, right? They don't care about, I mean, they do care about the simplified setups, but for them, the thing that's actually going to move the needle is when you can show reduction in biases. And we are still a few steps away from that. Yeah, but I think overall, I think it's, it's a positive community and they are quite receptive to many things. They also know that there's so few people that, not everyone can do everything. And so if somebody's trying something, they're quite open to it. Yeah, but that may be different in different communities.
Okay, we are a couple minutes past 1. So we'll wrap up. But thank you again, Drew, for a wonderful talk.